Rigid body dynamics. Rigid body dynamics is a core feature in game engines that simulate solid, non-deformable objects. How it works? Rigid bodies are objects that maintain their shape, such as cars, characters, or boxes. The physics engine calculates the motion, collision, and rotation based on real-world physics. Example uses characters interacting with the environment, objects falling, rolling, or colliding with each other. Example: Unity. Why it matters? Rigid body dynamics ensures that objects behave realistically, making interactions feel natural and immersive. Soft body physics. Soft body physics simulate flexible and deformable objects like jelly, cloth, or rubber. How it works? Objects are modeled as a collision of points connected by flexible constraints. These objects react to external forces by blending, stretching, or compressing. Example uses deforming vehicles in crashes, simulating cloth, rubber bands, or other flexible materials. Example: Unity with third-party plugins. Why it matters? Soft body physics add realism to objects that need to bend or stretch, enhancing immersion in simulations. Collision detection. Collision detection is responsible for detecting when objects interact or collide in the game world. How it works? The engine checks whether objects overlap or touch based on their shapes. Common techniques include bounding boxes, raycasting, and mesh-based collision checks. Example uses characters colliding with walls or objects, projectiles hitting targets. Example: Unreal Engine. Why it matters? Accurate collision detection ensures that interactions are constant and fair, maintaining gameplay integrity. Particle systems. Particle systems are used to simulate small dynamic objects like smoke, fire, rain, or explosions. How it works? Particle systems generate and animate individual particles, which are small objects affected by forces like gravity or wind. These systems simulate phenomena that require thousands of small interactions. Example uses simulating fire, smoke, and water effects, creating explosion, sparks, or magical effects. Example: Unreal Engine, Niagara. Why it matters? Particle systems bring dynamic immersive effect to life, adding depth to environments and interactions. Ragdoll physics. Ragdoll physics simulate the lifelike motion of characters after they lost control, like when they fall or are knocked out. How it works? Characters are broken down into rigid bodies connected by joints. Physics forces like gravity and collisions control how the character moves after a dramatic event. Example uses character collapsing after being defeated, realistic movements after explosion or impacts. Example: Unity. Why it matters? Ragdoll physics add unpredictability and humor to gameplay while making interactions feel more natural. Fluid simulation. Fluid simulation is used to model liquids and gases, creating realistic interactions in the game world. How it works? Fluids are simulated based on the properties of liquid, such as velocity, flow, and pressure. Fluid dynamics engines model how liquids move and interact with the environment. Example uses simulating water flow in rivers or oceans, creating realistic splash effects in combat. Example: Havoc physics. Why it matters? Fluid simulation creates a high level of realism, particularly in games that involve large-scale natural environments or water-based gameplay. Cloth simulation. Cloth simulation is used to simulate the movement and deformation of fabrics and materials in response to forces like wind or gravity. How it works? Cloth is represented by a grid of particles, which are constrained to mimic the behavior of fabric. The engine calculates how the fabric moves, falls, and reacts based on the forces applied to it. Example uses characters clothing or flag rolling in the wind, sails, or fabric-based puzzles. Example: Unity Cloth Simulator. What matters? Cloth simulation makes characters and objects feel more lifelike by accurately replicating how materials behave. Destruction physics. Destruction physics allow objects or environments to break apart or deform during gameplay. How it works? Objects are modeled to break into smaller pieces when certain conditions are met. Real-time calculations ensure their best behavior realistically, reacting to gravity, forces, and collisions. Example uses destruction of buildings in combat or explosions, breaking walls, doors, or barriers in environmental puzzles. Example, Unreal Engine, Chaos Destruction. White matters, destruction physics adds a layer of immersion, making environments feel more interactive and dynamic. Gravity and forces. Gravity and forces control the movement of objects and characters, simulating real-world physics. How it works? Gravity is applied to objects, pulling them downward based on their mass. Additional forces like friction, wind, or magnetism are also modeled to affect gameplay. Example uses characters jumping or falling with realistic gravity, objects moving under the influence of wind or friction. Example, Unity physics engine. White matters, gravity and forces make movement feel natural and provide the foundation for many interactive gameplay mechanics. Character controllers. Character controllers allow developers to recreate realistic character movement and interaction with the environment. How it works? Controllers manage player movement, including walking, jumping, and climbing. These systems also account for collision and physics-based interactions with the world. Example uses navigating obstacles in platformers or action games, interaction with terrain or climbing objects in explosion games. Example, Unreal Engine character movement component. White matters, character controllers ensure smooth, responsive movement and interaction, crucial for immersion in 3D environments. Watch this video to discover multiplayer game mechanic you need to know as a game developer.